Welcome, everyone, to the Wilson Science and Technology Forum. I'd like to welcome back Dr. Albert Moussa, the president and founder of BlazeTech Corporation, which is an R&D and engineering consulting firm that services the aviation and energy sectors of our economy. Albert spoke to us last year about the issue of um, air travel safety and in particular fire hazards associated with air travel. Today's going to talk about another dimension, uh, in particular hydrogen as a fuel in aviation in terms of its potential and challenges. Hydrogen is growing of importance in terms of a number of energy sectors in our economy. And so this is a talk that will provide a very broad perspective, but particular focus on hydrogen in aviation. Albert, welcome back, and I'll turn the floor over to you.
Thank you, Ron. Okay, so you've heard the title of the talk. Basically, I'm going to talk about the planned use of hydrogen in aviation, covering commercial airliners as well as air taxis. I'll talk about the benefit and the challenges of each. Also, I will compare hydrogen to other fuel alternatives. Then I will present a quantitative comparison of the crash fire hazard of liquid hydrogen versus carbon fuel. I'll end by making a few comments on other uses of hydrogen, particularly blending it with methane, as well as its use in transportation, cars, trucks, etc. This slide shows the projection of CO2 emission from aviation worldwide done by McKinsey and Company. The y-axis shows a gigaton of CO2 emission. And on the x-axis, you have the year. If you look at the year of 2025, where we are at, basically, aviation is responsible for slightly more than 1 gigaton of CO2 emission. But that's only 2.5 to 3% of all CO2 emission that are man-made. The problem is when you extend to 2050, you see that the projection by McKinsey is that the emission will triple. That is based on 4% increase per annum of aviation because the world is getting more populated and people worldwide have more money to travel. Now, if there are a lot of efficiencies, maybe 2% per annum, then the projection will drop, but not reach the target goals, which are of the order of, you can see two targets here. This one is 50% less than 2005 emission, which is about half or a third of a gigaton, or of course, the ultimate target of net zero with no emission. Now, again, the projection of McKinsey is if people use other fuel, such as SAF or hydrogen, then you can achieve certainly one of the targets and almost all of the target. Now, we'll see that if that's correct or not. And the fuel will be SAF, which is the sustainable aviation fuel. It's a synthetic fuel like jet fuel, and hydrogen, as well as other technologies they considered. Of course, the one thing missing here from that projection is if indeed one switches, the airline switches from Jet A to SAF or hydrogen, the cost of this fuel would be much higher. And therefore, that projection of the big increase to a factor of 3 will not happen. Anyway, so much for McKinsey. Now, let's look at what are the emissions from aircraft by various species. And of course, these emissions are happening at high altitude and produce contrails, which you could see in the bottom of the slides, and that's not desirable. Now, I'm showing the CO2 emission kilogram per kilogram and comparing jet fuel with green hydrogen. And all we're going to talk about is mainly green hydrogen. So obviously 14 to 0, it's a big change. Then if you look at water, water will actually increase if you use hydrogen. So you'll emit about 30% more than 6 to 9. NOx emission is in the order of ppms, and it's ppms either way, except that if the hydrogen plane is using fuel cells, not engines, then it could go to 0. Likewise for soot, it goes from traces to 0. Now, mind you that these 4 elements here that I listed so far can also trap radiation. And the bottom 3 constitute almost a doubling of the CO2 impact. So you can't only look at CO2 emission. Now, hydrogen, if you have it on a plane, and if it's a liquid hydrogen, then it has to boil off, meaning it has to evaporate to make up for the heat input to the plane over time due to the hotter air outside. And if you the estimate of that boil off is 1 to 3% per day from the tank. That means hydrogen vapor, pure hydrogen, will be shooting out in the atmosphere. Now, the global warming potential of hydrogen is 12 times CO2. So one has to integrate all of that in the comparison. Now, these slides compare. Now, okay, good. I just got rid of some of the pictures that are blocking me. These slides compare what will be an airport like if we switch from Jet A to hydrogen. So, for example, look at the hydrogen sphere. That's your storage tank. And that storage tank could be 1 million gallons. That's a lot of hydrogen. And it's always in a sphere because the sphere is the most advantageous in terms of heat loss because of the minimum mass, minimum area per unit mass. Now, of course, you will need also liquid hydrogen tanker to take the liquid hydrogen from the sphere to fuel the planes. And you could see the planes will have to be more bulky, and I'll talk more about that later. Now, to get the hydrogen to the airport, it might come by truck or by pipeline, and pipeline will be like 45 bars. These are high pressure gaseous pipeline, in which case you have to get the gas and liquefy it. So that's another process that you got to add to the airport, or come by ship. And there's only one ship built by Japan that you can see here. That's the Suizo Frontier, 300,000 gallons of liquid hydrogen. So that then will be a simpler transfer because it's already liquid to liquid, so you can pump it. Now that of course will favor the airport that are closer to shore, like Logan. Of course, if you know, when an LNG ship comes to Logan, the whole town is alerted, and there are cops all over in the water as well as on land to make sure there are no accidents, no attacks, no terrorist attacks on the ship. Because if these liquefied gases are released, there's a very large hazard. Now, there are other ways to bring in hydrogen to the airport, which would be with chemicals like ammonia or methanol. And then you would have to have a reformer that convert them to hydrogen and other gases. And in addition, you need a liquefaction system to liquefy them and be able to store them and then pump into the plane. So you see a lot of complications. And of course, ammonia itself is very hazardous, and methanol is a flammable material. So you could see a lot of impact on the airport. By the way, there is one airport in Canada, in the Midwest in Canada, which is considering all of that and starting to build the infrastructure using not green hydrogen, but gray hydrogen, which is the one that is, of course, you get from from methane reforming. I'll say one word about that. So at least they are getting prepared. Now, the other part of potential uses of hydrogen is what's called the urban air mobility. And you can see a concept put here by NASA. And what you have is a lot of very small vehicles. Some are manned, some are unmanned, and they're the one that are going to drop cargo on your home or be air taxis. Now, of course, for that to happen, there are going to be a lot of heliport at different locations within the city, and storage. Well, some will be hydrogen, storage of hydrogen, or storage of electricity. Now, the two kind of vehicles that I'm talking about are the cargo vehicle and the air taxis. Now, the cargo vehicles, you've seen them probably. They're all rotor driven. They're very light, 55 pounds to 100 pounds, battery operated, and unmanned. And some have already been certified to operate in suburban areas and in farming area. Obviously, because the FAA is concerned about their crashing and hurting people. Now, the air taxis will be much heavier, 1,000 pounds and up, and they can carry 2 to 5 passengers. But so far, the thinking is there will be a liquid hydrogen fuel because you need hydrogen in a very compressed, very, very small volume, and they'll be manned. Okay, here are pictures of the cargo UAVs. They all have turbines. You could see here the one by Amazon, DHL, Flactrex. Some of them have been certified already, and they will come to your home and drop the cargo in your yard. The air taxis are really different, and they kind of gonna replace helicopters essentially. That's the idea. But Joby is the biggest player in this, and they actually just bought Highfly, which had a very recent demonstration that went 500 miles. Most of these will be less than 500 miles, more like 100. And look at the design of the plane. In the Highfly, it's got two fuselage, and in the middle, another fuselage for the propeller. The pilot and the passengers will be on this side, the right side, and the circle indicates where the hydrogen is. So imagine how different is the design of the plane to accommodate the hydrogen. Now, if you look at Joby, the hydrogen tank is under the fuselage, and so is it in the other ones. Again, that tells you you're going to be really developing new designs just to handle the hydrogen. And obviously there are complications and how to prove that they safe, etc. Now we developed a model to handle the case where if you have a failed UAV like what you see on this is the cargo one, and if you lose electrical power, then all these propeller will stop. And the vehicle will start to fall down depending on its initial velocity and the forces on it, gravity, of course, and drag by the wind. So we did a force balance to predict where will it fall. And if you look at the point here, it shows that the path of a vehicle that lost power and then falls ballistically, so to speak, till it crashes. And a vehicle that starts with about 50 pounds or so, when it crashes, because of its velocity at impact, it will hit the ground with 2,000 plus foot-pound. Now, that's a lot of energy to not only kill people, but also to damage buildings. Now, to mitigate that, these devices, some of them will have parachutes. And if you open the parachutes, then you can land in different locations. Now, you see that we show the location by a little circle. And the parachute will make the circle bigger because once your parachute is on, then it's more dependent on the wind because now you have more drag. And therefore, as the wind varies and you have gusts, etc., then you might hit a larger area. And what's important is, when do you turn on your parachute? You can turn it on early or much later or not at all. And our model handles that, predicting in each case where does it fall, so that the driver of these UAVs, even if he is remotely, of course, but he with cameras can see what's underneath. He also knows the layout of the town he's over, to predict and control at least the starting of the parachute, to make sure you're going to minimize damage. And that's really what our model does for him, does all these calculations. Now, here are concepts for liquid hydrogen airliners, and it shows Airbus as well as Boeing. Airbus is a little more in advance of Boeing, because the whole Europe is kind of more alerted to climate change and the need for hydrogen. Although just recently Airbus is backing off a little bit, and of course whatever is being done in the US is going to be backed off because of Trump. Now you could see turbofans, 200 passengers. Now look at the redesign of the plane to have essentially a blended wing body shape to accommodate the hydrogen, because the tank is so large. Now in this second one, the Airbus, the hydrogen tank is in the rear after a bulkhead to isolate the hydrogen from the cabin and the cockpit, and it can only go to the engine. And again, this is a turbo engines, a propeller engine, excuse me. And Boeing, another turboprop with the hydrogen at the base, but not isolated, kind of like Airbus. But anyways, these are all concepts that are being examined. And it just shows you the big impact on the airplane design and construction. And that will take a long time. It will cost a lot of money. Now, when you talk about hydrogen, it's important to think about what source is it. And some of these sources now are given color. So we've been talking about green hydrogen, which essentially comes from a source like wind or solar, which provide electricity, but it's intermittent. Therefore, you want to be able to store it, and it's more efficient to store in a hydrogen as opposed to in batteries, and cost-wise as well. But to do that, you have to hydrolyze water, and then that gives you hydrogen, and that's your green hydrogen. Now, the gray one, you are using methane and steam, and basically you are reforming the methane through the gas shift reaction, and that gives you hydrogen CO2. So that's why it's gray, because it's not as clean as green hydrogen. Now, there are other sources of hydrogen, including naturally occurring, which comes from the earth or the ocean, but these are very new. And the old, of course, are coal gasification, which is not very desirable, or the blue one you can see here, which is, again, natural gas, like the gray, except you capture the carbon. So that is better from an environmental point of view. And of course, you could use nuclear power instead of electricity to drive the hydrolysis reaction and get green hydrogen. So these are the various sources. And what's important here is, when someone tells you, I'm going to use hydrogen, you got to ask, well, what's the source of hydrogen? And depending on the source, the cost will be very different, and the availability is different. And as I said earlier, that the airport in Canada is using gray hydrogen because they can't get enough green hydrogen, but that will allow them to set up the structures. All right. Now, the engine efficiencies between the turbine that you could have in a normal plane versus a fuel cell, which are really better engines for hydrogen, they take full advantage of the hydrogen, is quite different. You have gasoline and diesel. We're not going to talk about that now. But if you look at the gas turbine, There's a whole range depending on the conditions and the type of engine. So 20 to 30 is probably reasonable, and fuel cell 40 to 60. I'm going to take midpoint on these in my next slide, which shows the alternative fuels for aviation. Now, the top one is the battery, then SAF, I defined what that is, and liquid hydrogen. And you look first at the volume, let me just say the energy content first. And you could look at the energy content per unit volume or unit mass. And then the fourth column is the efficiency. And then these are numbers that I've taken out of the previous chart. And you can see there's a big difference in efficiency. The battery is 90%, SAF 25% because you're going to use an engine. Liquid hydrogen is 25 if you use the engine and you really have a thrust to push the aircraft. But if you use a fuel cell, you're producing electricity, which drives a propeller, and the efficiency is much higher, 50. Now, if you combine the efficiency with the energy content, you get these last two columns, effective energy content. And you could see that battery is way low. So battery will not be used for these large aircraft, only for those that drop little cargoes in your backyard. Now, if you compare SAF and liquid hydrogen, SAF beats it on volume, and because hydrogen is very light, and even when you liquefy it to liquid hydrogen, it is still lighter than jet fuel. But on energy, hydrogen wins. And whether it wins or not, by how much, depending on the type of engine. So it's a very complicated picture. Now, for an aircraft, both are important, mass and volume. However, because the SAF is essentially a drop-in replacement for Jet A, then you don't have to change the plane. And that's why the aircraft manufacturer, Boeing and Airbus, like SAF. And they'll use it if they can. That's what they tell me. It's just hard to find it. Now, of course, liquid hydrogen, that's a cryogenic tank, which means you're going to really have to redesign the plane. And the tank is going to be thick because of the insulation, as I said earlier. Compressed hydrogen is not being considered for these applications because it's too heavy. Now, what is sustained aviation fluid, SAF? It's basically a fluid that has the same chemical composition as Jet A, but produced by either crops, wood, oil seeds, algae, or waste from grease, from plants, fog. Fog is fat, oil, and grease. And these are all renewable, essentially. And they already, that is, if you use them, you're reducing the CO2. As a matter of fact, that's how you go CO2 neutral, because you're using stuff that captures CO2 from the air, and then you're using it for aviation. And as I must say that Airbus tells me that we can run on SAF, we can buy it. It's not produced in any large quantities. Now, in the Chicago airport, United Airlines is funding a large company as an investor to produce SAF for use by United Airlines, but that's going to take a few years. All right. Now, the interest in hydrogen aviation goes back to the 1970s, and it wasn't due to decarbonization, but it was because of the oil crisis, if you remember 73 and 79. And FAA had a rule that said no new system or fuel on the aircraft can be adopted unless you can demonstrate that the risk to passenger and public is no worse than current use. Okay? Otherwise, you don't get certified. That's very important. Now, at that time, in the late 70s, in the end of the 70s, NASA funded a study on a quantitative analysis of crash fire hazards to compare liquid hydrogen with carbon-based fuel. Now, I did that study. I was at Arthur DeLille at the time. And basically, they want us to focus on a failed aircraft during takeoff or landing, and it's survivable, obviously. If it's not survivable, then who cares about the fuel? Assume worst case, dump the whole fuel content and see what happens. And we looked at two scenarios, depending on when ignition happens after the release of the fuel. Now, first, I'm going to talk about some general safety consideration before talking about the scenarios. First, comparing liquid hydrogen Jet A. Hydrogens have some issues that don't exist with Jet A, like hydrogen embrittlement. Being a very small molecule, it could penetrate into the aluminum structure or any metal, and that make the aluminum stiffer and or more brittle if you want. It's also a cryogen, so you have the boil off. It's have a very wide flammability limit, 4 to 75% on a volume basis, compared to Jet A, 0.7 to 5. So you could drop Jet A and may not ignite. It's not easy to ignite, actually, but it can ignite in a crash situation. The spark, the energy needed for a spark ignition is 10 times less for hydrogen. So if hydrogen leaks, it's going to ignite. That you could be sure of, unless it dissipates. And I'll talk more about that in a minute. The other thing is the hydrogen molecule, because it's small and its thermal diffusivity is very high, the potential for leakage is high compared to Jet A. So you see, it's tough to compare the two. One thing that is not known to most people, and these are really new findings from 2 years ago by the FAA, is that most material flammability are, of course, highly flame resistant. Otherwise, you cannot put them on the aircraft. Okay, that makes sense. Now, if you're using hydrogen in a tank and it leaks slightly inside, what the FAA test determined, as you could see on the left side, these are tests where you could put a flame to the material in the plane, and it will burn. But when you pull the flame away, it has to stop burning, self-extinguish within a particular time, and the flame height should not exceed a particular value. Now, if the test is done in 1%, you see kind of that burn region increase a little bit over 0%. If you go to 2%, it goes much higher. Then look at the chart, which goes from 0, no hydrogen, all the way to 4%, which is flammable. Now, flammable, obviously, hydrogen will burn. But the point of the graph is if you have very small amount of hydrogen, it can help other things burn. And you could see that the burn, the duration of the burn goes up and exceeds these horizontal lines, which is the minimum. And likewise, the flame length goes up and exceeds the horizontal red line. You get the picture? So you don't want hydrogen to leak in the plane, obviously. And of course, if it accumulates, you got other problem. But even if you tell me, well, I got a sensor, but the sensor can only measure 0.5%, it's not flammable, no good, because it could do other things. All right, now let's go back to the scenarios. The one where you don't have immediate ignition. So you've dumped the whole content of the aircraft, and hydrogen, because it's coming at 20 degree Kelvin, and the ground is at about 300 Kelvin, or 70 F. The heat transfer is very high, so it's going to boil like crazy. It's a cryogen. And depending on the wind, it's going to flow, you could get a plume, and it might dissipate if there's no ignition sources. However, depending on the wind, it could go somewhere, and if you're in an airport, it could go to the building or downtown. These plumes could go long distance. And the confinement of buildings and the plentiful ignition sources in building, be it light or cars or whatever in the city, can be an issue. So the big question is, where does it go? Will it be confinement? And there is no comparable issue. The plume from Jet A is dirty. It might put soot around the area. You have to clean that up, but it doesn't have that hazard, the plume hazard, which is fire and explosion, particularly if you have confinement. So, oh, by the way, we developed a model at BlazeTech that analyzes that specifically, including will the hydrogen react and burn or detonate. And we work it for hydrogen or any other fuel all the way to explosives. So that model could have been used in the FAA study, except it wasn't available then, but it can be now. That model is called ADOA, atmospheric dispersion of reacting agents. And most dispersion models just assume that what comes out is inert, not going to react with anything.
Working here?
Is going to be basically it's going to dilute, of course, because it's mixing with the air. All right. Now we move to the second scenario, which is immediate ignition. And what I'm showing here is what happened actually on Continental Airlines. And you could see that the fuel got spilled, and you have a liquid film on the bottom below the aircraft, and it's burning, get that huge plume. And you could see people are going down the chute area. So they're evacuating the plane as this happens. And the faster you can evacuate, of course, the better. And you have people around it. So that's what happened in a pool fire scenarios that engulfs the plane. And here we can do a one-to-one comparison between hydrogen and fossil fuel, or carbon fuel. And that was then selected for the NASA study. At the time, Lockheed had actually a design for a regular airliner using liquid hydrogen. This was a 400 passenger, Mach 0.85, 5,500 nautical miles. That's your typical plane that gets you across the States or across the Atlantic. And if you look at the plane here, every time I use my pointer, the thing jumps. It's a bad thing, but anyways, I'll try to make it not jump. All right. So you see that shaded area in the back of the plane, and there's another one in the front of the plane, and that's where Lockheed, in their wisdom, put the hydrogen tanks. These are cryogenic tanks, liquid hydrogen tanks. And they did a lot of work to design them to make sure that the right size, mass, etc. However, these tanks will isolate the cockpit from the cabin, and that's not acceptable in aircraft design. So other planes, if you remember, the Boeing and the Boeing and the Airbus planes had different designs which overcame that. But at the time, Lockheed, that's what they had, and that's what they gave us. All right. Given the fact that the design of a liquid hydrogen tank that I just showed you is so different from a Jet A, it was very difficult to do the comparison. But we overcame this difficulty. First, let me tell you about comparing the two cases. The amount of volume on the aircraft for Jet A is 1/3 hydrogen. Okay, hydrogen is more bulky. The mass is the other way around. So hydrogen is even less than 1/3 of the mass on board. If you look at the total content of fuel that will be consumed in that 5,500 nautical miles, that's in terajoule. Hydrogen is 20% less than Jet A. So actually, you're saving joule, which is really ultimately is the way to say it. You don't care whether it's coming from Jet A or hydrogen, it's less. And I presume that's because the plane is lighter if you just compare the weights of the two fuels. So that's a big plus for hydrogen. Now, the fuel tank design is very different. In Jet A, it's a single wall. It's actually, they call them wet wings, meaning the wall of the wing is the container of the fuel. While in hydrogen, you have double wall with insulation, and its location is different. So if you're looking for identical crash landing conditions, meaning the plane is going to crash with the same velocity, angle, deceleration, the terrain is the same, the damage to these two aircraft designs and fuel tank designs will be very different. Different amount of fuel will be released at different rates. So the question is, how do you do a side-by-side comparison given these difficulties? Okay? And because of the early stages of the design of the Lockheed aircraft, we didn't have any details really to assess these. That stopped people, but we went forward. Yeah, go ahead.
I'm just curious. The materials of construction of the fuel tanks for hydrogen fuel, what are they? What are the materials of construction?
Well, you got the insulation, and you could have aluminum, but it has to be coated in particular ways to minimize the brittlement.
Right.
But if it's going to fly, it's going to be aluminum.
No.
Can't have steel.
But you also need cryogenic facilities, right, to keep the liquid there?
No, not really. That's what boil-off is. So the boil-off maintains the temperature of the fuel, but you lose fuel. So heat goes in, evaporates hydrogen, evaporates liquid hydrogen. So you got more gases, pressure goes up, and you got a valve that opens.
So you allow for that.
You allow for that. You can't have, now on the airport, and I showed you the spheres, you don't have to do that. So you could take, you could have, you take the vapors, you take the vapors, refrigerate them, put them back. And that's a very expensive way. There's better way I could tell you about than what they talk about. Anyways, sure. So just to say that it was difficult to do the side-by-side comparison. So we found a way that actually worked. And you'll see that after I'm done. So our approach was to do modeling, and that was the objective. Of course, you couldn't do anything but modeling. You couldn't test these things in terms of airplane design, etc. So what we did in the approach is to assume in the comparison, same volume coming out or same energy for both fuel. Now, we know that's not correct. I just told you. But we don't know what they are. So we said, okay, we're going to compare them on a one-to-one basis that way. Let's see what happens. And now for each of these releases, we calculated the resulting pool fire in numbers. You know, NASA wants direct comparisons. So we calculated the thermal output, the duration of the fire, the thermal dose, which is the integral of the heat flux over time onto the fuselage, and compared the liquid hydrogen with actually 3 carbon fuel of interest at the time: liquefied natural gas, kerosene, and gasoline. I think the interest in liquid natural gas disappeared because it still have carbon in it. This is so it doesn't help. It doesn't help decarbonization. It helps in many other things, and we use it here in Boston. We get LNG, and we use it. All right. So the model here is basically a flame that develops above the pool, and the flame will have some sort of cylindrical shape. The inclination of the shape could depend on the wind. You know, if it's just burning, it goes straight up. If there's wind, it could bend. And in both cases, we have that film of fuel that has been dumped. Now, for jet fuel, that film is getting heat from above, from the flame. And that's make it evaporate and burn. For liquid hydrogen, it's getting heat from the flame as well as from the ground. And that's very important because that delta T, delta temperature, ground to hydrogen is very high. So we calculated that to see how much it will evaporate. And there were correlations to say, okay, if it evaporates at this rate and it has the following fuel properties, it's going to have that height. And of course, things burn at different temperatures. And depending on how well they mix, we could get the radiation flux and then the heat dose, which is the integral of the flux over the flight duration. And we did that. We did that for the 4 fuels. And what I'm showing here is the pool fire diameter and and the flame height. And you could see that we have different points on that. And let's just see what happens here. If you look at the triangle, which is 10 cubic meter per 10 cubic meter of hydrogen released, then you get that point on the liquid hydrogen curve, which has its own diameter and height, which is very different from the points on the other one, which has different diameter, different height. Every fuel does its own thing, so to speak. So that's kind of the results of this calculation. The other is the pool fire duration. And again, liquid hydrogen lasts a very short time compared to the other fuels for the reason I gave you already. And if you look at how they stacked up, it's kind of related pretty much to temperature and volatility. The easier thing to burn early, obviously, is going to burn faster or earlier. The easier thing to ignite, because of higher volatility, is going to burn faster or shorter duration. Now, this is what we did for each fuel, which is we calculate the emitted flux, which is this curve, which depends on temperature and burning rate, the emissivity, how much of that emitted flux goes on the fuselage or the tarmac, and then the heat dose, which is the integral I told you about of heat flux over time. So the heat emitted is kilowatt per square meter. When you integrate that, you're going to get joules per square meter. And that's what the units here, it happens to be megajoules just because of it's so much. Now, we can compare that integrated thermal dose for the four fuels. And you could do the comparison in different ways as a function of the released amount. And that's what I'm showing here. And you could see, again, hydrogen is below the other ones. And interestingly, you know that each point on that curve is a different accident. No, I should have said that. Every point is a different amount of liquid released. We don't know which accident. But it didn't matter, actually, what liquid you assume, because hydrogen came out to be always lower than the other two. So given the same test conditions, we may have a point for hydrogen around here and a point for the other fuel elsewhere, but it doesn't matter because hydrogen is below. And that's really what we're trying to do. We have to show that hydrogen will cause no more damage, is less risk than to passenger and people than these other fuels. So that difficulty we had because we couldn't analyze, given the same accident, how much fuel will come out, was resolved by looking at the results of our analysis. Now you see here, this is megajoule per meter square. That's the dose. Now, you could also look at the dose, same dose, as a function of not the amount of the volume released, but the energy released. So how you multiply volume by the heat of combustion of each. And hydrogen was also lower than the others. So it actually does justify our conclusion, which is for crash pool fires, the hazard from liquid hydrogen fueled aircraft is less than the other four fuel, or no worse, anyways. That's for the FAA. The presentation I made was for instantaneous releases. If it's 5 cubic meter, dumped immediately. The whole tank, dumped immediately. We also did it for continuous releases, and the results are very similar. So now we have a direct, now what's needed is a direct validation of these hydrogen results. Of course, these were done in 1980. Well, the report came out in 82. That was started earlier. There are other fire scenarios that one has to keep in mind. You can't just talk about the pool fire. Obviously, leakage is very important. Confinement is very important. Okay. So much for hydrogen aviation. And because of the interest of this group, I thought I could do some comments on other uses of hydrogen. One is blending hydrogen with natural gas. And the gas company are really pushing for that. They are funding hydrogen projects. Why? They want to maintain their network. If decarbonization say no methane, what's going to happen to that whole network? So they would like to do is blend them. And of course, in the limit, if we ever get to that limit, is you push hydrogen instead of natural gas. Now, there are issues with that, of course. So that's one item. The other is transport vehicle. And then you could use hydrogen as a liquid or gas, depending on the vehicle. And then use of hydrogen in industry. So I'll comment on these. First, hydrogen is so important now in the US and worldwide to the point where the DOE has decided to create 7 clean hydrogen hubs. And these are different locations in the country. You could see where they are. And they are giving about $1 billion per hub to spend in maybe 5 years or so. 5 have already been signed during the Biden administration, and 2 were not, and we're not sure what's going to happen. But these 2 were in red states. So there is a chance they'll continue. By the way, New England did bid and didn't get it. Okay. Well, let me just say that the purpose of the hub is to overcome all these infrastructure issues that I said. First, you have to produce the hydrogen. Then how would you store it? When do you use it, gas versus liquid, et cetera, et cetera. That's the purpose of the hub. And then small difference, of course, depending on which hub. And California is way ahead of everybody on these. They actually started years ago. All right. So back to blending hydrogen with natural gas. First, let's just look at a general natural gas system. Gas comes from either wells or LNG delivery like we got in Boston. It gets processed, and then it gets stored or pumped. Now, that means you have big compressor station pushing the gas, and they use gas to push it. That's it goes to the city. You see a branch here that goes to power generation or large industry separate from the city. Once it goes to the city, now the pressure drops significantly. I think it's about 1,000 of PSI at the compressor level, about 200 PSI at the city level, and then it goes to commercial, residential. When it gets to your home, it's inches of water. Of course, you don't want the high pressure of gas. You have high pressure of water, 60 PSI, but not gas. So that's kind of the standard distribution system. And if they combine hydrogen to it, you see that hydrogen will be coming again from solar or wind, and then it's going to go hopefully directly to the consumer volume or to the city requirements. That's kind of the vision, but it will be compressed. Now let's look at blending of hydrogen and natural gas. Now this is hydrogen in the gas form. If you compare the mass, the joule per kilogram. Joule per kilogram doesn't matter whether you're gas or liquid. Obviously, mass is a mass, okay? But by volume makes a big difference, and actually depends on the temperature and pressure. But if you look at the hydrogen per unit mass, obviously much better than natural gas, is more than 2 times. When you look at it per volume, then it's the opposite. And what's important for the distribution system is the volume, because these compressors push things. And the bigger the volume flow, the more you have to push. That means more pressure loss in the line, and you need better compressors, or bigger compressors. Now, the issues are still issues of embrittlement, leakage, flammability. And of course, I mentioned that earlier, that they're the same. But then the compressor station will have to be upgraded, depending on where you're going to blend. And the combustion equipment on the compressor station. So let me review that very simply. You need larger compressor, to make up for the pressure loss for the lower energy per unit volume, or you use the same compressor and you derate your system. Now it's pushing the same amount, but you're not getting as much energy. These compressors are usually driven by gas turbine. And by the way, the gas turbine are also used in power plants, and then they burn methane. These are the peaking power. And people are doing a lot of studies to see how much H2 you could handle and still burn in a gas turbine, in a combustor. And there are different results, like 25%, the combustor will work, but you need some control. But of course, what's going to happen is the temperature will go up, which can produce more NOx. And the company GE is working very hard to make sure these issues are resolved. And you need an emission control strategy as well. So there's some modification, but it can work. The other option is kind of a different mode of operation for a gas turbine, which are called lean premixed combustion. Now the gas turbine usually has a diffusion flame. They're not mixed. You kind of inject the fuel and the air, and they mix in the combustor. But in the lean premixed, they have advantages. They produce less NOx. But you can only use 2 to 5% if you're going to put in hydrogen. So you see, it's a lot of technology that's actually being worked upon today because people are very serious about that. As a matter of fact, there have been several projects worldwide. First, there is no international standard for H2 blending or what percent of H2 and NG. It doesn't exist yet. So people are trying different things. The UK have been testing up to 20%. And again, in specific areas where you control things better, etc. France, 6 to 20%. In Dunkirk, Dunkirk, you remember from World War II. Why they selected that, I have no idea. But Italy, much less. In the US, lots of research, but no specific percentage that I know of. I've heard about 15 in some places, but it's all research. All right, so much for blending hydrogen and natural gas, which is a very important subject in terms of hydrogen usage. Now we've switched to other usage. The hydrogen car and the fuel cell, if you remember some of the efficiency curve I showed you, is roughly 2 times more efficient than an SI engine. Because it doesn't depend on Carnot cycle, if you know thermodynamics. And it doesn't emit CO2. So these are big advantages. But the question is, does it make sense to use a fuel cell with hydrogen on a car? And I'll address that. There are safety issues, of course. And then limited refueling locations. Now, California, being ahead of everybody, had already several, maybe several hundred, perhaps 1,000, I've forgotten the real number, of hydrogen cars in operation. These are the Mirai. However, they're all dependent on hydrogen coming from a single facility in California. And when the facility had an explosion in 2019, there was no hydrogen to refuel them. And Toyota sent these hundreds of owners, loaner cars, to operate, to run, because they felt responsible. Okay. Nicely from Toyota. Now let's compare a hydrogen car to an electric car. If you look at all the way to the left, the ideal in the decarbonization is you have energy coming from solar and wind, but they're intermittent, and you want to store the excess when they're running so that you could use it when they're intermittently not running. And I'm showing 2 branches. If you put that electricity, these are kilowatt hours, right into the battery, and the battery drives the car, in terms of the motion of the car, meaning electricity to motor turning, it's 90% efficient. You got other losses, but now if you compare the same thing just from electricity to car for hydrogen, you gotta first produce the hydrogen. So the electricity and water will go in an electrolyzer. That produces the hydrogen. Then you have to store it, etc. And then you gotta send it to a fuel cell. And then the fuel cell produces electricity for the car. But the electrolyzer is roughly 50%, 40 to 60. I use 50. Fuel cell, 50%. So what end up reaching the car from that, let's say, X amount of kilowatt hour of electricity that we started with is 25 compared to 90%. So I ask you, why would you ever have a hydrogen car? Well, Toyota, of course, is aware of that. I mean, they're no dummies. And they decided to get into hydrogen, and they started with the car. Now there's thoughts that the car was a mistake, and they're going to trucks and larger vehicles. Now here, let me just do a few comparisons just for information. The car weight for the Mirai is heavier than, say, a Camry. And that's because the fuel cells are heavy. Fuel tank capacity is larger in gallons because the weight of the hydrogen, but the weight of hydrogen is much less. And that's a plus. The empty tank of hydrogen is heavy. And that's really what kills it. And these hydrogen tanks are not the insulated cryo tanks, but these are more carbon fiber reinforced plastics to minimize weight. But they are running at 10,000 psi, 700 atmosphere or bars. That's a very high pressure. And you always worry in a collision, what would happen? Will you leak enough? And there are, by the way, videos on the web done by Tesla to show you that if you collide, you're going to lose the whole plane. Obviously, they're pushing the electrical cars. And the comparison is same mileage, same refueling, which is good. Of course, there are other differences, and I'm not going to go through all of that. Some of you have electrical car. You kind of know what that would be. The cost is higher, obviously, for hydrogen. Now, regarding some of the tests, I mentioned the Tesla one, which is obviously promoted by Tesla. Now, these are tests done by the University of California in Coral Gables, by a professor who I presume was funded by either DOE or a hydrogen company. And what they're comparing here, hydrogen and a gasoline car, in a simulated collision or failure. And for the hydrogen, he failed the pressure relief valve. So he had a nice jet because being pushed by 1,000 psi. And the hydrogen is ignited intentionally, and you get this big flame shooting up. And if you're outside, it dissipates. No one gets hurt. Even the car gets not heated much. The temperature inside the vehicle while this was happening was livable, was not that high. And it only lasted 2 minutes to empty the tank, right, because of the high pressure. Now, when he repeated the same thing by puncturing a fuel line in a gasoline car, you see the mess that is, and obviously, if you didn't get the people out, they are killed. But again, these comparisons are tough to do, and looking at one comparison is not good enough. You gotta look at a whole bunch to justify the assumption you're making. Now, there are protection on the car and in the fuel station. So during refueling, there's a very tight seal between the nozzle and the car where hydrogen will go in. And it's locked as long as there's pressure in the hose. They're protective devices to prevent you from driving off before you disconnect it. And these are on the car and the dispenser. And they're leak detection devices too. So you see a lot of protection, obviously. Whether that's good enough or not, that's another issue. But you could see it's not simply a simple replacement. And that's why the airlines would like that SAF, because literally it's a drop-in replacement. Of course, we'll see how well that will work. Now, in case of collision, the tank will automatically isolate themselves on the car. And of course, the other thing is you got to provide special training for the firefighter and the first responder, kind of like what was done for electrical cars. But till now, the car fire happens, and the fire department arrives, and they're not sure what to do, etc. It's not clear. So even doing that is not easy, but that's needed. All right. So much for cars. Now let's look at larger transport system. Ships and trains. Now they have more space. And if you can have a large tank. And then if you have a large tank, then you can go liquid hydrogen. If you do it with pressurized hydrogen, the penalty is much higher because of the weight of the tank. But ships and trains are being designed today with liquid hydrogen. And this is, again, one of a kind in many places, but in different countries, it's happening. When you look at the trucks, it's a big issue in the sense that some people, Toyota pushes it, Honda has also a design, but Tesla also is talking about trucks, and it's a big competition because there are pros and cons of each. But it's interesting. Obviously, the hydrogen people talk about decarbonization, while the EV people come up with all sorts of things, less noise, the fact that you're lighter, so you won't affect the hard top of the highways as much. Of course, that's even true with gasoline versus electrical cars. But electric cars will be very heavy, electrical truck. So that's why hydrogen's really pushing it. Anyways, I think it's going to take a while to see. Probably they're going to both be built, and it took a while to see which one really wins. Here's an example of the storage in a heavy-duty truck. This is a 10-wheeler or so, and you see the engine in the front, and it includes fuel cells, and the back is hydrogen tanks. And look at how high that is. And I'll show you a picture with a person. Well, I had him stand just to get a sense of scale. And there's 6 tanks. This is basically the same tank design in the car. It's going to be used, but 6 times more. Okay. And here is a fellow who, in the meeting, just stood by. That's a Honda truck, chassis and all of that. So they're serious about it. They're building it. They're pushing it. Okay. What's that? No, actually, well, that's actually, you're right about that. The issue of size is very important because it's taking payload. Okay, and same in the plane as well. Okay, so this basically shows you the powertrain and the storage. All right. Now, so much for cars, trucks, transportation. I'm going to make some comment about hydrogen use in the US. 1,600 miles of pipeline of compressed hydrogen in the US, mainly in the Gulf of Mexico, to serve the petroleum industry. And you need hydrogen for cracking petroleum. And along with that, there's 10 million metric tons that are used annually in the US. Most of it is for the petroleum, but some for the fertilizer. For the fertilizer, use hydrogen and air, the nitrogen in the air, to produce ammonia. So be careful now. People want to use ammonia as a carrier of hydrogen. And say, but that came from hydrogen initially. And how was the hydrogen produced? If it came from decarbonization, from electrical, then you got to carry all this processes, and the efficiency term to make sense out of it. Having worked myself in the industry during industrial energy conservation, I was very conscious of all of this. Where is the leak and where is the good efficiency versus not? We were doing back in the 80s what people do today, they call it sustainability. Well, we did everything. We didn't call it sustainability. We looked for alternate fuels, but not the same as the ones now, hydrogen and decarbonized fuels. And we looked at efficiency, etc. So we did decarbonize, we did sustainability back then. Now, hydrogen is used also in food processing, metal processing, rocket fuel, welding. I believe there's a lot of potential in high temperature processes because if you burn hydrogen, you get a higher temperature. And in some processes like glass, steel, you need it. And people are working on that today, but they're not getting as much attention as all these other hydrogen projects. Now, there have been hydrogen accidents worldwide. And there is an organization out of DOE called HIAD, Hydrogen Incident and Accident Database, and they collect all sort of information. And it's operated jointly with the European Commission. Developed in 2004 and contain a whole bunch of profiles of accidents. Some were fatal, several were fatal. Even 2010, there was 7 people dying in a refinery that used hydrogen. But generally, if you look at the statistics, it's 20 accidents per year worldwide. And then when you look deep at these accidents, happened to be 43, 352 were directly related to hydrogen. And the 81 were really the hydrogen burned because something else ignited stuff. So it was, hydrogen was a victim. But still, out of the 352, about 300 were fire and explosion. Okay, so you can't just say hydrogen will come out, it's light and air is going to dissipate. Well, it depends on what come out where, what temperature, under what conditions, and what else is around. Now, the safety record in the petroleum industry has been good. As a chemical, the mitigation and protection method have been developed. And the best practices are available, and they're followed in the petrochemical industry. And actually, what I presented for the crash of planes, given that I ignored how much fuel come out of the plane, given the accident detail, what I presented would work very well for stationary storage tank. You know, if you got a tank that big and it spills, you gotta get a pool fire of that size, it could disperse, etc. The plume, the fire will be applied. And this, I think we could learn a lot from the petroleum industry and apply it to hydrogen, to the new uses of hydrogen. Now, as a fuel or a fuel carrier, some people like to call it that, I think that's semantic. And in new industries, they don't have knowledge or practice with these mitigation and protection methods. And you need to adapt them. What works in a stationary situation may not work for aircraft. And after adapting them, you need to adopt them by the new workforce, which means you have to retrain the people at the airport dealing with hydrogen, etc., and even the UAVs if they use hydrogen for air taxis. And the residential use poses new challenges because how are you going to train people if they're having hydrogen and natural gas coming to their home and it could leak? And so that's an issue that deserves attention. Because of that reason, I have prepared a course on hydrogen, and it's offering in August of this year. And it looks at the exceptional properties of hydrogen. You know, you can't just say, well, I know gases. Hydrogen has a kind of some special features. For example, under some conditions, has a negative Joule-Thomson coefficient, if you remember that from thermodynamics. We look at hydrogen as a fuel, accidental releases from pressurized versus cryogenic tanks. We look at fires in the open, or inside structures, explosion, and what kind of hydrogen safety assessment can be applied in transport or in basic stationary facilities. And the big concern I have now is the data centers. Because of artificial intelligence, data centers are coming everywhere, and they are going to use up so much energy. I would think probably if you look at the utility they come back with per unit energy, it's probably zip. They're going to make money per unit energy, but not utility from why they're doing it. But anyways, one has to be very careful, because if you get these IT people managing energy systems, well, they need training as well. Okay, well, thank you for listening, and I'm happy to answer any questions.
Well, thank you. I just have to say that was some really comprehensive and insightful presentation.
Thank you.
And I have so many questions.
Okay, go ahead.
But I'm going to open it up, but I want to start with two questions.
Mm-hmm.
You know, I have done some work on materials of construction of hypersonic vehicles. This is in relation to the U.S. Space Force.
Mm-hmm.
And, you know, these are vehicles that fly at, say, Mach 5 when we get to
Mach 5 and up.
Yeah.
Yeah.
And you talked about the use of hydrogen in commercial airliners like the Continental flight. Sure. Is there a risk-benefit analysis that should be performed? If you're talking about national defense, that's one thing. If you're talking about commercial aviation, do you have any reservation about commercial reservation using hydrogen as a fuel? You're the expert.
Okay,
so
well,
I want your opinion.
I'll tell you, and I'll answer it by a real fact, which is when we wanted to replace these ozone depleting fire suppression systems worldwide, because of the ozone hole, if you remember, and all that. The agents in the refrigerator were replaced. There was a clock, you got to do it by a particular time. They put similar requirement on airplanes, and then they relaxed it. In other words, they couldn't find anybody to replace hair loss. Okay? And I think the same thing going to happen with airplanes, meaning decarbonization is a big push. And if you look at airplane, I believe is like 2 or 3%. I may be wrong about that, but let's say I said 1 gigaton of CO2 emitted today. What is it in the whole country? Anybody knows how many gigaton? Let's say probably 12, 20, something like that. So again, it's a few percent. When you talk about decarbonization, the people doing it want to do everything. But that doesn't make sense to me. There are risk benefit, as you said, and you got to first go after the easiest, they call them the low-hanging fruits. So get that first. And then that's going to be big improvement after you've done that. And then there may be some fruit that you like to admire, but you cannot grab in real life. And likewise in this one. Yeah. Have I answered you?
Yeah, no, that's a good answer. Yeah. No, I accept that.
And I presume some economists, etc., are doing calculation like this.
Yeah.
But I'll tell you, when it comes to cost, if you remember, I didn't mention cost at all in these, because when people do cost, you could go all over the place. Even if you ask today, what is the cost of a kilogram of hydrogen? Well, people pushing hydrogen will tell you, oh, you could get it for $6. Others tell you 13. It's the economists will do it, moving target. So they will do the analysis. Someone, DOE must have the same question you have.
Yeah.
And I have people, they have to put people on it. I'm not sure I can believe them, to be honest.
Let me ask one additional question. You mentioned that there are 1,600 miles of hydrogen pipeline in the south, in the Gulf Coast area, carrying hydrogen. You know, I felt for a long time that we could use the existing pipelines to transport hydrogen. pipelines that are carrying natural gas or whatever, with one exception. And that is the quality of the welds on these pipelines. So my question is the pipeline that you mentioned in the sub, was that an existing pipeline or is it new, and are the welds super inspected? Because they are the weak point in these, and they're very susceptible to improvement.
Yeah, wells are always the weak point in it.
Yeah.
Okay. Of course, in addition to wells, are the seals, the gaskets, and all of that.
Yeah.
But this has been going on for quite some time. So it is working. How they got there, I'm not sure. Okay. So whatever problem, they resolved it because they cannot afford to let hydrogen leaks. But occasionally they have problems. And out of these 430 accidents or so that I mentioned, there could well be failure of a weld, failure of this. But they've been learning and mitigating things.
Because I think they're solvable problems. You have to identify it and then apply a solution. But if you identify it first and you're rational about it, you can do that. So let me open the floor. I know there are other questions. In the room, Walter, you have a question.
Yeah, actually, no, I have 4 questions. So in regards to putting hydrogen into natural gas, I'm actually totally opposed to that because of the number 1, the atomic number of hydrogen. It's a tiny molecule and it can go through steel, it can in brittle. So it doesn't seem to be a safe alternative. I mean, right now we have natural gas leaking
anyways.
and it's going to be more so. And then when you deliver it to the homes, you got new meters, you're going to have new stoves. I mean, new heating equipment. So I'm not a big fan of that. But let's talk about cost.
Wait. I agree with you, by the way. And I had just one liner that when it comes to commercial use, that's another story.
Okay.
Residential use, that's another story completely. Yeah.
But let's take a look at. I know you approached the cost, but is cost? Let's talk about relative terms of cost versus a current jet fuel versus SAF, and then and now hydrogen. So are we talking exponential increase in cost? I know it's hard to pin it down, but it's certainly going to be more than today's jet fuel.
Okay. So today they talk about hydrogen being $10, $13. Okay, maybe more. SAF is not available to pin a cost yet, but is viewed as the holy grail, not hydrogen. And that because the airline do not want to redesign their planes. They look at it as a drop-in fuel replacement.
So is SAF being used in some airlines right now?
Being tested. I don't know if it's being used in any airlines. I know that United is planning to use it.
Right.
But okay, they are funding as investors the facility to build it. So all they have for now is some pilot scale results. Now, when the facility comes out, they're going to test the darn thing. And the prices could be different from what they initially thought, but they're investors anyways. So there's a lot of effort. What I've heard from the engine people and Boeing is if we have it, we'll use it, no problem. I mean, they've had it in small quantities. But Airbus told me specifically, we cannot buy it. We cannot buy it in quantity enough to.
Okay, but in relative terms, I presume that
Be higher.
The jet fuel is going to be cheapest.
Of course.
SAF is going to be
More expensive. Right.
And then hydrogen is going to be
Could be correct.
So
No, hang on. Forgive me. Even if liquid hydrogen is cheap, it's used by the airliners bring other costs, which is redesigning the plane and rebuilding the plane. So you can't just.
So you get fixed cost.
Okay.
Right.
It's a little more complicated than just the cost of the fuel.
And then the other complication.
May I just add? So even if hydrogen was cheaper than SAF when it's really produced in quantity, blah, 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 they might go SAF because it's a drop-in replacement.
Yeah. And so the other part of the question is the CO2 production in life cycle. Meaning right now it's gray hydrogen, which is produced from natural gas, and that's produced in CO2. Yet there is, maybe you can use alternative sources to produce hydrogen and electrolyze it, but that's not a whole lot. We're about 1% of the production right now. And so the production of CO2 right now, is that going to be greater than using this jet fuel? And barring any kind of natural source of hydrogen, which I've read that maybe there is some natural hydrogen somewhere.
Right.
So what about the CO2 production versus jet fuel?
Well, what we know is the following. They analyzed jet fuel in detail, how many alkanes, how many aromatics, blah, blah, blah. And they want the SAF to match that. If you don't match that, you're going to have to redesign the engine. Okay? So it's the same. So basically, if you look at my table, how much CO2 is produced, I had SAF/Jet A, because I didn't know what SAF would.
But you had hydrogen at zero, but it's not really at zero if it's gray hydrogen.
No, of course. That's correct. I did say that my stuff I'm showing is green hydrogen.
Yeah, but what if you have gray hydrogen?
First, how did you produce the methane, the natural gas?
CO2 and hydrogen. You could react CO2 with hydrogen.
Yeah, correct. So if there's hydrogen in it already, but that's a sink of CO2 if it's coming from the air. You're asking a question I don't know the answer for. It's complicated, okay?
This is a good conversation.
And it's evolving.
Good conversation to have over a couple of beers. Let's turn to.
And when it comes to cost and what's better, it's an evolving thing because.
Let's turn to Michael. Michael, you're online. You're mute. There you go.
Yeah, I got a problem. I'm working.
You have some echo, Mike.
There. Not this, is it?
Yes. Okay. Biomass is oftentimes overlooked. Can you hear me now?
Yes, I hear you.
Can you hear me?
Yes.
Can you hear me?
Yes, you're good.
Yes, okay. Biomass is oftentimes overlooked, but let me present this to you, Albert. We have processed a certain biomass in the past under very highly controlled pyrolysis conditions that take into account the thermogravimetric analysis of the particular biomass, which is available in billions of tons without competing with food crops. And out of that biomass, we produced a fraction of fuel that has a freezing, a cloud point of minus 92 degrees Fahrenheit. Now, I've just sent you a video of a test tube of that fuel that was pulled out of a block of dry ice for 20 minutes, and you can see that it still flows. But basically, aside from the fact that we can pull that fraction out of the biomass, we get liquid fuels, including that one. We have a balance of fuel from which we can pull hydrogen. We produce a gas which has hydrogen in it, along with some methane, and we produce biochar. So effectively, we can produce SAF at a 92 below Fahrenheit that will also produce hydrogen that sequesters CO2 from the atmosphere so that we actually have carbon negative SAF, and there are billions of tons of available biomass to produce this product. And I think it would be a good complement.
Well,
It would be a good complement to the work you're doing with hydrogen.
Yeah, Mike, I know what you're doing. And
I work on pyrolysis for my doctoral thesis, and I got a publication that's basically everybody quotes. When I had the SAF sheet, I showed that one way is really biomaterials and the other were wastes, okay? So everybody knows that SAF can be produced from wood and the like. The problem with what you're saying is typically the collection of these biomaterials. That's always a problem. As a matter of fact, in the 80s, there was an outfit out of Boston somewhere, a local guy, who was pyrolyzing wood and paper and things. But he literally had his pyrolyzer on a truck to move his truck to the source of waste or materials because he was so aware of the problem of collecting the stuff. And, he lasted about 3 or 4 years and then he closed shop. So two-part to what you said. I know one can get SAF out of what you have. I know I could get hydrogen from what you have, and I think we had previous conversation on that. The difficulty in what you're doing, and I don't know how you're going to solve that, is the collection assembly of the biomaterials. That has been kind of Achilles' heel in this process.
I would tell you that the particular biomaterial that's available is available over millions of square miles and can be processed through my mobile system on a very decentralized basis. So rather than having to produce it at one facility that could go down in an explosion, you could have hundreds of facilities spread over millions of square miles using this readily available biomass without competing with the food industry. And per unit of weight of this biomass, I suspect we can produce 40% of these oils, which then we'd have to distill some of the very high, low temperature oils out. But we also would be producing a considerable amount of gases, which can be used to generate electricity to produce more hydrogen on a highly decentralized basis.
I think this is a good point to remember that we're going to make a field trip visit to Michael's plant sometime when you're ready, Michael. But I think it's a good conversation, but I think we move on a bit now.
I just want to make a relevant comment.
Yeah.
Mike, I'm glad you're going away from ethanol, whatever, food-based fuels. And I remember DJ Wilson told me when I was a student that it takes more energy to produce ethanol than the heat of content of ethanol.
Absolutely.
Okay, so all along, I've always avoided going for the food for that reason, as well as competing with food, which raises the price of food, etc. But it just happened that the ethanol lobby is so powerful from the farmer and the like. And that's why I'm hesitant to answer the question that was asked by Walter, because at that level, there are so many factors outside of technology and engineering.
Progress.
Let's go ahead.
Yes, Mike, thank you very much for your talk, by the way, Albert. Very nice. Got echoes. Yeah. Don't know if I go further away from the microphone, it might help.
Good.
Yeah, I'm wondering about the safety issues. You noted about 480 accidents on a relatively, I don't know how much of a scale we're talking about, but if we were to scale it up to a national level or an international, global level, how does that compare for example, to the oil and gas industry and or to to just normal gas events, because we hear several times a year of explosions in households and so forth. And the other question I have is, you mentioned that hydrogen is an enhancer of materials bursting into flame. And what I'm afraid of, I suppose, is what does that imply? My goodness, what does that imply relative to material, to say what you're going to do at airports and so forth, to ensure that any fire created by hydrogen essentially is going to be limited? Because it will bloom out far more than fuel would.
So let me answer the first question, which is the petrochemical people have a lot of other extremely hazardous chemicals on board. They're dealing with hydrogen, with acetylene, with a lot of double bonded and triple bonded chemicals that can react very easily. So hydrogen is not the worst thing they're dealing with. And oftentimes, the big accident is not a hydrogen accident. It's others, like, for example, the what happened in the UK on the platform, the drilling platform, Alpha something, if you remember that killed a lot of people, etc. So that's why don't have to worry too much about their use of hydrogen. They're using a lot of other things just as bad, if not worse. Okay? So that's the first one. Now, on the second question, that's why the concern that Walter has and I have, and I didn't discuss it much other than saying this is kind of another issue, residential use in residential, because any usage other than the plane will not get that attention that I talked about of looking to how does hydrogen increase flammability of other materials. And let me tell you, knowing how things are done, we'll never get there. Meaning the people in the construction business and the make burners and the pipes and whatever, they care less about what's around. Unlike in an aircraft where you're saying, I don't want flammable material on. So the best thing is to avoid it, to be honest. And now I can't go very far in these things because I haven't studied it. But for example, stoves now, they have inductive coupling, which work much better than resistive stove. Now, how does that compare to a gas-fired stove? And maybe that's the solution until one day we discover that inductive coupling gives you a headache or causes some other DNA thing. What can you say? You got to do the best you can and go with the punches.
I understand that. I'm just thinking about if you got a national, if vehicles are going to be using fuel cells, then there are fuel cell station, hydrogen stations all over. And how do you guarantee and make sure that
that's
the safety of those?
Right. Yes. So they've thought about it and they have some precaution, but sooner or later, the precaution will fail and we'll have an accident. Yes, that's undoubtedly. And of course, the collision. You can never say we're not going to have collisions. It's going to be someone who's drunk, who's careless. And yeah, you could have these protection things, but I can imagine a collision that basically breaks the tank.
But I see Wayne's hand up, and I'll give you.
Can't hear you, Ron.
Go ahead.
You're muted.
Go ahead, Wayne.
I just want to ask a question.
You're on, Wayne. If you can you hear me? Wayne?
Go ahead, Wayne.
I have a question.
Okay.
Does your efficiency comparison between EVs and hydrogen-powered cars, how does it take into account the energy required to compress the hydrogen to 10,000 psi?
Actually didn't have that. Correct. No, that's good. Didn't have that. I looked at very simply the efficiency of the electrolyzer and the fuel cell. And you're right. It takes a lot of energy to compress to 10,000 psi.
So I wonder, can that be done in the depths of the ocean where using the weight of the water to compress the hydrogen in order to reduce the amount of energy that's required to compress it to 10,000 psi?
No, but you still have to pump it all the way down and then bring it back up.
You
And
can
then you need the
generate the
technology to do
hydrogen
it.
down at a very large depth in the ocean.
If you can get it from there, okay, that would be an advantage, of course, kind of like Walter was talking about natural hydrogen. Natural hydrogen would be nice. That's even they call it white hydrogen. Okay? The point is, we don't know enough about all that to really do a direct comparison.
And I have one other question. How about when EVs become much more common than they are now, they'll have to deal with battery disposal. And with hydrogen, you don't have to deal with that.
Yeah.
You don't have all these landfills with batteries that weren't able to be recycled.
Good points, of course. And just to add to your point, MIT did studies that said if you have so many VEs running around everywhere, you're going to run out of lithium, or you're going to run out of the materials you need, and that's going to be a big problem. But who knows? I mean, it's an issue, of course, but who knows, because people are looking for other battery technologies, not involving lithium.
Yeah, I mean, there are strategic issues with supply chain for those metals.
I agree, strategic issue, correct.
Yeah. Then I think we'll call this session to a close. I want to thank Albert once again for a very, very insightful talk. Hydrogen is, when you think about it, water is a great source of hydrogen, and it's everywhere. If we can figure out how to manage it safely, effectively, then it can become a major part of our fuel energy mix. But there are a lot of questions,
right,
and we're not there yet, but we're moving in the right direction. So thank you,
good.
Albert.
You're welcome. And I'm going to be around for a few minutes, and that's a plug for in-person meeting. Come on down sometime.